use of the small satellite features. To start with, I repeat the new graph I had yesterday for the optical small satellite part. He has the three different resolution kinds: spatial resolution, spectral resolution, and temporal. I talked about the increasing of the spatial resolution. He started in 2006 with less than 1 meter runs up in distance. Spectral resolution, hyperspectral, starting in 2001 with microsatellite having a hyperspectral imager with 64 channels in the distal range. And I stressed the point that the temporal resolution is the key point for small satellites. It's the only way to construct affordable radios and emissions. And I gave two examples, or one example is specifically the disaster monitoring constellation, and there's Rapid Eye, and you have of course the Roxanne 3 mission, but that's an optical small satellite mission, optical mission. And I want to come to three examples. One is the optical constellation, expressing the constellation formation part. It's not here. And then we come to magnetic field measurement and gravity measurement. Then all fields which have been possible with small satellite applications. Let's start with the DSC, disaster monitoring constellation. 5 satellites from China, Turkey, United Kingdom, Nigeria, Algeria, all microsatellites. Beside the 18-1, that is a bit larger because it has an additional 4-meter channel on the satellite. And as you can see here, you have seen that all the 5 satellites are in one sun-synchronous orbit, and they are turning around the Earth, and the Earth is rotating beneath that orbit. And so the satellites are arranged like a curve in this orbit, and due to the rotation of the Earth, we have this wide swath which can be constructed that way. So with that, we have a real wide swath can be constructed. And think about the performance of such a constellation. One of these satellites has a ground sample distance of 32 meters and a swath width of 600 kilometers. Compare that with Landsat, that has a ground sample distance of 30 meters and a swath width of 185 kilometers. So that is for a microsatellite country. And now we are combining 5 of them, bringing out the wide swath width, covering the complete Earth every day, and can find any point on Earth every day, provided the cloud situation is allowing imaging. If we arrange the small satellites or the satellites in different orbit planes, then we can have a dynamic observation of any point of the Earth, provided we are going for daytime imaging only, and we want to observe between 9 a.m. and 3 p.m. when the elevation angle of the sun is good enough to have a good contrast. Then we need just 3 satellites to image every 3 hours, 9 a.m., 12 noon, 3 p.m. If you want to have an hourly repetition rate, then 7 satellites, and you can even go to 20 minutes repetition rate with 20 satellites. So that's quite amazing what you can do with this kind of constellations. Let's come now to the magnetometer constellation. It's a SWAT, that is the name of the mission. It was selected as the fifth mission of the ESA's First Explorer program, already in 2004. And it is to map the magnetic field of the Earth. And each spacecraft is equipped with a vector field magnetometers and has some additional instruments to make a precise attitude and position measurement. And the key performance parameters have to make sure that the precision of any measurement is good enough to separate the different effects which are combined with the measurements in orbit. The overall performance is organized with 3 satellites. 2 are flying in a 450 kilometer orbit at the beginning, and it's jumping down when time goes by. They are flying side by side. The separation is 1.4 degrees, that is about 160 kilometers, and to measure the east-west gradient of the magnetic field. And there's another satellite flying with a 3 to 9 hour local time shift in an entire orbit to help to separate the different effects. Launch was done in 2010. And that's amazing what you can do with a magnetic field measurement. You can measure the interior of the Earth, the map of the core flow, determine the core dynamics, understand core mantle coupling, and its implication for Earth's rotation. You can do a 3D imaging of the mantle conductivity and determine the remnant and the induced magnetization of the lithosphere. And concerning the Earth's environment, it's to determine the position and development of the rotation belts and its near-Earth effects, and the time-space structures of magnetospheric bands for the current systems in all time scales. That's to do the possibility to construct the following system, which is arranged in a very specific way, as you have seen. So altogether, that is what has been achieved: high precision and high resolution measurements of the strength, direction, and variation of the magnetic field, complemented by the precise navigation of the accelerometer. The measurements, of course, the magnetic field measurements is a basic measurement. It provides the necessary observations that are required to separate and model the various sources of the geomagnetic field, provided a unique view inside the Earth, as explained before. That's how it works. You see the 2 satellites side by side, and the other one crossing close to perpendicular. It's a very nice, it was a very nice mission, and scientists have been excited about the results coming out of that. Coming now to the next small satellite formation in this definition I gave yesterday, RACE. That is a joint project from NASA and DLR with the United States and Germany. It was launched in March 2002 to measure the gravity field of the Earth. Time was 5 years. There's planned to have another RACE mission, the follow-on mission, which is hooking up on the results coming from that mission and bringing better results and answering new questions which came out of space has two identical spacecrafts, and the original measurements are done using the intersatellite distance measurement combined with GPS and accelerometer measurements. Here you can see the work share for the mission from different partners, and the orbit. Yeah. So, in short, what's going to be measured, or what has been measured in this case, the gravity field of the Earth is variable in both time and space, and is an integral constraint on the mean and time oriented mass distribution of the Earth. The science data from GRACE mission was used to estimate the global models for mean and time variable Earth's gravity field, approximately every 30 days for the 5-year lifetime. And the GRACE mission's results are derived from the three parameters I mentioned before: the intersatellite distance measurement, and the position and accelerometer measurements coming from related instruments. So the variations of the GRACE studies include that the changes to the surface, deep currents in the ocean, and that's amazing what we can do from space. Runoff of groundwater, storage and land masses, exchange between ice sheets and glaciers in the ocean, and even the variation of mass within the Earth. Another goal of the mission was to create a better profile of the Earth's atmosphere. The Earth's atmosphere is a gravity measurement. And then how it works. Here is indicated the intersatellite distance measurement. You see the first satellite is attracted by this massive gravity hump. Yeah, so you get an impression how it works. And from these kinds of measurements, assisted by GPS and accelerometer measurements, you can really determine the right position of planes coming from the components of the Earth. And at the end, it turns out that the Earth is not a sphere, it's kind of potato. The height differences are accelerated by thousands. So coming to the conclusions. Small satellite complement the existing satellite systems. I give you 3 examples. What we can do additionally can be done with the guides. Optical small satellites can provide high spatial and spectral resolution. And the small sats provides a unique possibility for affordable constellations and formations. From the spaceball point of view, it's the most cost-effective way to meet the actual incoming information requirements is to pursue the development of smaller, lighter, lower power, high performance satellite that can act as constellations. That's what I wanted to convey to you. Thank you very much.
Thank you, Sanders. Any comments? Okay.
First of all, I must say that I really enjoyed your talk here yesterday. This morning, this talk is And as you already know, the multi-system is pretty good because when it comes to special resolution, which means we can get daily data. I'm pretty interested in long-term time series data. That's one of the major reasons why I'm using all this data. But I still have two major problems. Special resolution, and then the messy data contents, primarily because of the cover. Now, you have constellation system using your micro, pico, whatever you say. I think you can get rid of those two problems at the same time. As long as you can get, say, one scene every, I don't know, several hours, maybe.